Okay, so thank you all for staying for the last day of the conference. So some of the things that I'll talk about, I think won't need as much of an introduction, so I'll breeze through some of those. But feel free at any point to jump in and ask me questions. I'm perfectly happy with that. All right, so most of the work that I'm going to talk about was done at the University of Virginia in Olivier Pfister's group, and a lot of it was in collaboration with some folks at RMIT, so Nick Menachouchi and Raphael Alexander. But currently I am at LPS, so to give a little bit of some, shameless plug, we have a lot of in-house research in different types of qubit technologies, but we also fund a variety of different types of research. And recently, the LPS Qubit Collaboratory in the Qubits for Quantum Foundry program, we partnered with Lincoln Labs, Intel, and HRL to obtain fluxonium qubits and quantum dot spin qubits that we can use ourselves and test and also distribute to other research groups. So we are hiring both postdocs and full-time positions. If you want to change or anything, talk to me afterwards, or if you have students, feel free to email me. So, okay, so I like to kind of talk about, when I talk about photonics and quantum computing, I like to show a brief timeline just to kind of, make us all feel a little bit good about the progress that we make. Because honestly, if you think about it, the amount of progress in quantum computing technologies over the last several decades has been actually quite astounding, especially if you consider that the laser was really only invented in 1960 and Feynman proposed quantum computing in 81, and then, among other things. And then what's cool, this conference has shown me that there's a lot of cross-technology ideas that have been cross-pollinating and actually can be used. So for instance, like the original dual rail encoding in photonics is now kind of, oh, look, maybe we can use it in superconducting circuits and maybe it's cool. So part of my talk, I'll introduce some really interesting things that can be done because of photonic architectures. And maybe you guys have some ideas about maybe it'll be useful for other technologies as well. And so then recently, of course, there's been, these quantum supremacy claims, which may or may not hold up with advanced classical algorithms, but yet it's still interesting technological achievements. So first, kind of motivating the case for photons, like why use optics? So first, optics you can do at room temperature, excluding perhaps detection. And you can utilize multiple degrees of freedom, time, frequency, phase multiplexing, and then natively network non-local systems. So a lot of what I'll talk about at the first half of this talk is not just continuous variables, but what optics can do and interesting things. And so if somebody comes up with a, I don't know, lossless superconducting switch box, then maybe some of these ideas can be transitioned, or, I don't know. That's not my field, but we can hope. So, and then why continuous variables, and in particular, why GKP? Well, optical systems give us these really nice scalable deterministic entanglement when you talk about like squeeze states that you can then send through certain crystals or time multiplex and get thousands or even up to millions of entangled modes coherently. And then Clifford gates become very simple to implement once you have GKP states because it's just homodyne detection and displacements. And then thanks to some results by Ben and others that if you have GKP as a resource state, then non-Clifford gates actually use Gaussian states as a resource. So you use the vacuum, you do quantum error correction with a GKP state on the vacuum. It gives you the magic you need for non-Clifford gates in this encoding, which is really cool. But so we all know Bosonic encoding GKP looks roughly like this. They're cone with translation symmetry. And one additional thing I want to mention is there's been some talk this week about using erasure protection. And if you use full analog information of the GKP code, you get the best information, but that might be difficult for a decoder. So if you just maybe truncate and you say, I flag something that's unreliable, you might get some returns without using the full information. But I also, just to caveat, I talked to Nick Menachouchi earlier this week. So these results here are still preliminary. They're still updating the actual numerical nature of that improvement and what actually that is. But so just if you have specific questions on that, I talked to him. But it's still an interesting thing that you could do with GKP. Now, of course, we know GKP states we can make them in superconducting circuitry. We can make them in trapped ion systems. But optically, from an all-optical approach, it's really hard. And there are a lot of approaches to do this. Some of them, most of them are non-deterministic. And this is a challenge. So One of the interesting approaches is you take a Gaussian boson sampler. So you take squeeze states, input into an interferometer, and then you do photon number projection on the output, except for one mode. And if you tune your parameters and then you wait, you post-select on the right photon number, you can get fault-tolerant GKP states. Now, other than the fact that this is very low success probability, the other thing that you need is you do need the ability to resolve photon numbers with detectors, which is hard, and it can be done. And people have shown that you can do it for large photon numbers, even up to close to 100. But first, they're very relatively slow detectors, unless you use many multiplexed, say S and SPDs. And then loss is a big challenge. So the second half of my talk, I'll try to motivate perhaps new ways we can think about doing this, where you only need low photon number resolution, maybe like 1, 2, maybe 3 photons. So we'll see. But first, in order to motivate a lot of the use of optics, I want to go back a little bit and talk about measurement-based quantum computing, which I'm sure most of you are familiar with, but just in case you aren't, I want to touch on it again. So, right, you could do a circuit-based model, but we don't really want to do this with optics because photons travel very fast, and you don't really want to hold them for too long, because then you lose them, and so you don't want to hold them around to do gates. So instead, it's much better to do cluster states and do measurement-based quantum computing. So you do some sort of thing where you take and you do all of your entanglement up front. So you have some sort of resource states, you entangle them a nearest neighbor style. And then what you can do is when you do measurements, individual single qubit measurements will now apply gates. And there's some overhead in the number of qubits you need to consume to do this. And you can now think about your logical information as kind of traveling through teleportation throughout this sort of substrate. But it's nice because if you just change the measurement basis, you can do all of your gates this way, and you don't need to do any additional entangling between two individual of your physical qubits in your underlying kind of substrate. So this is really cool by Rossendorf. And just to give an example of kind of how that works, you can take your initial arbitrary quantum state, you CZ it to a plus state, you measure your psi, and you get teleportation up to some gate that based on the measurement result. You can undo it, and you've teleported psi. So that's the smallest cluster state, just 2 qubits, CZ them together, and it's teleportation essentially. But with this, you can actually do arbitrary unitary rotations, and so now this is still all in the qubit sense, and I'll get to the continuous variables later. But if you choose your measurement basis correctly, you can do any single qubit gate unitary with just 4 measurements. And just because it'll become important later, I want to, for those of you less familiar with optics, I'm going to go through how you kind of implement this kind of thing. And so you might have a state generator that's pulsing some sort of optic signal, and then you might say send some through a delay, and so it kind of loops back around and comes in line with the next state being generated. And you get some entanglement that propagates back in time. And then you can do detection. And so what basically you can change that measurement basis based on previous results. And so this is why I like also from a physical perspective to write circuits right to left instead of left to right. So I also prefer that convention. Thank you, Nick. Because if you think about it, right, I like to write when I'm drawing diagrams that I have my kind of beginning of my experiment on the left, and I kind of go through to the right, and then I detect. But if I actually look at how the information flows at, say, T0, I measure it, but then T1 is the next one in the line, and so it kind of teleports back in time or forward in time, or however you want to think about it. But what I can do is with the information flow goes this way, but I can tune the measurement results of subsequent detections, so that way I can maybe change what types of gates I'm applying to my information. So now this is a kind of a simplified version, because if you want to do this with optics, it's better to do it with linear optics. So you do all of your nonlinearity up front, and then you want to say use beam splitter interactions. So effectively, you get something that looks like this kind of quad rail or this dual rail thing. So you've got, sorry, not dual rail. You've got these pairs of macronodes where your quantum information from a single piece of quantum information is encoded within those 2 different modes. And so it looks kind of like this quantum information equivalent of single nodes going back if you do everything mathematically sound. Okay, so how do we use this for quantum error correction in optics? So like I said, we don't want to, we don't hold them. So you're not going to do a surface code quite the same way as you would if you had matter qubits, where you could say, lay them out and then do parity checks on the same thing over and over again and kind of build this up. So what's really cool is what Rossendorf and Harrington and Goyle wrote was you can actually foliate this. So imagine you have this like static qubit surface code type of thing, whether it be toric code, planar code, whatever you want. And you can pull it out into a third dimension in a foliation pattern. And so this is really amenable to optics because you can do you can make time one dimension. So you can teleport your information back. And so now instead of your parity checks being plaquettes and tiles in your static lattice, you actually have these kind of width one kind of cubes as being your parity check. And so it's interesting, you see the x's that are here, right? So actually, if you were to look at your stabilizers, it's really x, z, 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 z. But if you do that on all faces, the z's cancel out. And so it's really cool because you get this thing where you have a primal lattice, and then you have its dual, which is the other one. So actually, you really only need to, for quantum memory, you really only need to do x measurements everywhere. And then your decoder takes care of this. You have to think about the fact that, okay, well, I have a primal lattice that I decode separate from my dual lattice. And then you can actually, there's several ways that people propose to do gates. You either do braiding with defects or you do lattice surgery. There's a lot of things. But the point is, optics gives you the freedom to be able to do time delays and actually do different things even beyond this. So for instance, I could think about extensions, and people have at PsyQuantum, where instead of just foliating that surface code that you think of, you can actually make lattices that arise from non-foliatable surface codes, essentially. So like you can't defoliate these back into surface. And so they look complicated, but why might you want to do this? Well, it turns out that with different types of lattices, you might get different thresholds to certain types of errors. So as you see, you do these different curves, you've got a weighted erasure threshold that changes based and different from your polydepolarizing threshold. And so why might this be useful is if we kind of tie this back into things that other people have talked about this week, is if you can encode maybe in a dual rail underneath or some other thing, or take your GKP and turn it into an erasure. If you can turn some of your errors into erasure errors, then it might be advantageous to use different types of these lattices. So there's lots of freedom that you can do. The other thing that's just really interesting with optics is this kind of concept called active volume, which is relatively new. And this is now stepping like down the line a little bit. This is assuming you have quantum error correction working. This is more at the algorithmic level. But it's really interesting because instead of looking at normal circuit volume, what you do is you have memory modules and you have a workspace. And so it's really, you just have different registers of qubits. And you say now, well, I have some sort of region where I really only use my circuit for a small period of time. So what I'm trying to do is figure out ways to, you swap from one to the other. And this really only works if you have some sorts of non-local connectivity, but limited non-local connectivity. So perhaps there's some other interesting things that can be applied to, say, neutral atoms, like people talked about earlier, or if long-range connectivity with, say, like trapped ions, or if you do get a magical, switch box that's superconducting. I don't know. But if you weren't aware, it's interesting to think about. And the other thing that you can do with optics is you can kind of rasterize a resource state. So if you imagine you want to do like surface codes, instead of say, I'm going to pulse whatever my optic state is for all the qubits in the surface code, I can play games with time. So what I can say is, well, I say I pulse my resource state really fast, but now maybe my gate time is an integer multiple longer. So I kind of hold them for different times. And so then maybe I get away with using fewer resource state factories, but I have to have longer gate times. And so there's trade-offs here, just interesting games that you can play. And then you could use, say, optical switches, which are pretty lossy and not great at the moment, but you never know. Okay, so now onto the actual continuous variable part. So I think most of you know this, so I'm going to skip it. Yeah, so it's basically like you can take, plus states and you can switch them all into continuous variable, like momentum eigenstates. That's kind of the equivalent. And these have been made very large scale experimentally, which is really cool. Okay, and also I'm the camp where I think Wigner functions should be blue when they're positive, but you know it doesn't matter. But if you make a good figure, always get as much mileage out of it as possible. So that's why I'm showing this slide. So what's known in optics, which is really cool, is actually if you do photon subtraction on a squeezed state, it's a very good approximation to a cat state. And so the way you might do this is you might take a squeezed state, you send it through a beam splitter, it's very weakly reflected. And you send that tiny amount of light that you reflect to a photon number resolving detector. And it turns out that to a very good approximation, the number of photons you detect there is approximately the number that are just subtracted. So it's like you apply the annihilation operator to your state. And the higher numbers that get annihilated from your squeezed state, the larger the amplitude of your cat. And the squeezing changes slightly, but it is still squeezed to a degree. Okay, so this is known. And then my goal is to say, okay, can I take the fact that we know how to make small cat states with optics, and we know how to make these large continuous variable cluster states? Can I kind of put them together? Because I don't want to then take a bunch of squeeze cats that I've made individually and then try to stitch them together. That sounds like a pain. Can I do it the other way around? And so the idea is I want to try to embed cat states into cluster states after I've made them. So to do this, it's instructive to think about kind of how the actual gate operations are applied. So again, right to left, if I have some psi and I've CZ'd it to a momentum eigenstate, and this you can think of this as this is what comes out of your initial optics experiment with your nonlinear crystals. You've got a whole bunch of these, and psi could just be to begin with another momentum eigenstate. It could be or something that's teleported down the line, but you've got a bunch of these. So what I do is I do a homodyne measurement. That's what I'm denoting with my m sub p. I'm measuring in the p basis. And what that does is it teleports my psi to the next mode, and it applies both a Fourier transform, which is just a phase-space rotation, and a displacement or a shift in x that is dependent on the measurement result. And I know that because I have that classical measurement result. So when I write the circuit, I'll write it like this. And so also I can write my circuits like this. Okay, so what if I instead modify my homodyne detection? And instead of just doing homodyne detection, I do photon subtraction first. And so what I'm going to do is I'm going to use my approximation that it's roughly like I am applying the annihilation operator to the n power. And okay, so now I want to see what this circuit does. Well, it's kind of annoying because if I write my annihilation operator in terms of Q plus IP, I want to commute it with my CZ gate, which isn't super fun, especially if I subtract a lot. So what I can do is I can actually kind of write this as a superposition of many different circuits, like so, where I've got this, Q plus IP part that comes over, and then just a Q part only on the bottom rail. And if I, suppose for now, I post-select on a measurement result of m equals 0, which I will relax later, but just for purposes of instruction, it's easy to see what happens. You actually get directly a Hermite polynomial in Q applied to your input state. And so you can do a polynomial gate. So now, you might wonder, where does the Hermite polynomial pop out? But if you think about it, photon numbers, the wave function is really just a Hermite polynomial with some exponential kind of damping factor. And so what's happening here is because of the weak photon number detection that I'm doing, I've got this photon subtraction, really I get away with not having to apply this kind of damping operator because I'm using the resource of the squeeze state in the other mode. And so it's kind of like you're projecting onto a photon number state and applying that as a filter, but then you're also getting more squeezing to get rid of what would happen. And so you really get this polynomial Q, which is really neat. So just like applying photon subtraction to squeeze states gives you cat states. Oh, wait, sorry. Different slide first. Okay. So kind of show this how this would work. I'm going to denote this green square as me doing photon subtraction followed by homodyne detection. And so what I'll get is this kind of result where I've got, say, suppose I just measure one photon at a time. Then I've applied Q minus the measurement result. There's a Fourier transform that comes from the teleportation, and then this X shift just from the measurement of the homodyne detection. And I can undo that with the feed-forward displacements, which I have to do actively, depending on where I do that, and the circuit can change. I might just do that before the photon subtraction. I can talk more about that later if you have questions. So then I can just do a homodyne result here. And the reason I just do that is because I want to get rid of that Fourier transform. So I want to re-rotate my state. And I can then undo that additional feed forward. And now I've got FF, and so it'll rotate around. And then I can do it again, and so on, and so on. And eventually I get rid of all my Fourier transforms. And I result in just these products of Q and some measurement results. So if I detect more than one photon, it's a higher power of Q. But what I'm going to do is I'm going to tune my beam splitter subtraction such that it's not likely that that happens. It's likely that I only detect low numbers of photons, so I don't have to have a strong photon number resolving detector. And this is what I was going to say. So it turns out not only does subtracting photons from a squeezed cat state give you from a squeezed state give you a squeezed cat state, applying Q to the n to a squeezed state gives you a squeezed cat state or an anti-squeezed cat state. But actually, doing some numerical simulations, the full circuit is a little bit more complicated. So I'm using the arrow to denote a beam splitter. And we also have to include finite squeezing, of course, because before I was talking about infinite energy, and that's no fun. So what I'm doing here is I did some Monte Carlo simulations essentially, and I'm showing random stochastic results, both in the homodyne measurement and in the photon subtraction result. So the black number in the upper left is the iteration number when I go through and do this. And the red number on the bottom is the number of photons that were subtracted in that instance. So you start with the squeeze state, top left, and I didn't subtract any that time, so it just maybe gets a little less squeezed. And then I subtract one photon, and I see I get some red in my case for non-Gaussianity. And then I didn't subtract a photon for several rounds. So the non-Gaussianity kind of gets washed away by the finite squeezing Gaussian noise a little bit. But then, I get a pop of another photon subtraction. So it's this probabilistic kind of random walk. But over time, it kind of, you see, it converges to a better cat state. And what's really interesting is this persists even in the presence of Gaussian noise due to finite squeezing. So on the left here, I'm just showing, okay, if I were to keep doing this, and the reason I have just a plane rotation in the middle is because if I didn't, I would get subtraction. I have to realign my cat state fringes essentially. So I get the subtraction to build up and make me a cat. And I get, so that the bottom left plot is a little misleading because I don't show the variance. I just show like the mean of the cat amplitude. So actually the variance kind of narrows down as you go out too. So what you're doing is you're getting a more stable cat. But what's really interesting, and it's a little messy, is the plot on the right here. So what I'm showing is, suppose you just have a cat state that you've injected in your cluster state. You start with a cat. And what you do is if you just teleport it along, you would imagine that finite squeezing and the Gaussian noise from the teleportation will start to kind of bring down your cat. And that's what's happening in this top left plot. And I say plane teleportation. So what happens is if I look at the distance from the origin in these circles is the cat state amplitude. And as my amplitude, as I teleport along, my amplitude kind of comes down and I get a phase of the cat that kind of gets a random hit. And if I start with a really big cat, as the one right below it, it can the phase can go all the way around, but it slowly goes down to zero. Whereas on the right, because fun acronyms are fun, so we call it phantom. It doesn't really mean anything. It's just a fun acronym. But if you start with a cat state and then do this photon subtraction assisted teleportation, so you're doing photon subtraction before homodyne detection, actually you kind of get this stabilization of your cat amplitude with a random but knowable kick to the cat state phase, which basically means it's switching from an even cat to an odd cat. And the bottom right, which is interesting, you're starting with a cat that's too large for the squeezing in your system to support. And so it kind of goes down to some level and then it kind of stays. Okay, I think I am running out of time. So the idea is you could do this in a cluster state that you've already made, and you could bring them and eventually use breeding protocols to turn cats to G-gate. And Vigan and Terral did a really cool result. And this is just some math I didn't expect to want to go through anyway. We can talk about it later if you want. And there's some really cool links to phase estimation, actually. So you can actually say, well, if I use a cat state, I can actually map a cosine function onto my continuous variable states. It works for macronodes too. And there's some cool extensions where you can actually do say, all right, well, I want to maybe make a larger cluster state that's like a little bit more complicated with some, say, periodic modularity. And then I want to say maybe embed cat states in different parts of the cluster state. And then maybe what I do is I collapse it down onto, say, like a Rossendorf lattice. And so I've collapsed in my cat states down. And so then maybe I can use them for quantum computation. Okay, and so then just to wrap up, I wanted to say that photonics give you some really interesting ways to play with multiplexing with time and space degrees of freedom, where you can kind of maybe interleave. You can do a lot of interesting types of lattices that might protect against different types of erasure errors, and maybe some of these things can be mapped onto other quantum systems as well. The non-local connectivity is a really promising avenue, and you can actually have potentially very fast gate operations with high speed. All right, thank you, and I'm happy to take any questions and to talk later.
Do you have any idea what the effect of the extra kind of like phase operator in the Krauss operators for photon detection does? That you made the assumption that it was just a to the n, but it typically includes this e to the I.
We include that, actually, yeah. So that I simplified it for the sake of understanding, but if you actually, it's okay, it's hidden in that f of n. So that f sub n there, if you actually include, so you include finite squeezing, and here I'm doing a realistic actual beam splitter before photon number detection. And so it's all in that, and it's a mess. And so what this is the function of only Q, but that function has some additional phase damping in both quadratures, and there's some Hermite-like nature to it. And then you get the finite squeezing effect coming here at the end. So it's all in that, and this simulation encompasses all of that. The only thing this doesn't encompass is loss. And I didn't talk about that because, I mean, it's obviously very important. What happens, because I imagine you'll care, basically, this doesn't perpetuate. This perpetuates if you just have Gaussian mode. If you have loss, what happens is you sometimes aren't sure the parity of the photon number you detect there, so you get some washing away of fringes, as you might imagine. So you actually get, you get some amount of time, you get better non-Gaussianity, and your cat gets better to a point, and then it kind of starts to decay as the loss starts to erode in your system.
Can you comment a bit on what happens if you have not photon number resolving detectors?
Yeah, so if they're not resolving, so what you want to do is, it depends on the amount that they can resolve, right? So you might say, instead of it just being a click 0, 1 detector, I have some 0, 1, 2. And what that'll do is it's a similar effect to loss, but slightly different, because it's going to give you some mixing of those higher photon number probabilities. But you can mitigate it slightly, because if you tune that beam splitter such that the probability of detecting more than your detector allows is quite low, then you get this kind of very small error effect. And what it essentially does is it's the same as not being sure what the parity is, and so you wash away some of your non-Gaussian.
So I'm curious if the parity is always even for the cat when you prepare it in this way.
So no, it is not. It might be the case of this example that maybe it looks like it is. Yeah, so like here it looks like it's being kind of, so right. So what happens, there's a key thing that I kind of glossed over, is so after you do this, you get this measurement dependent shift from your homodyne detection. What you want to do is, if you commute that through your circuit, and so you would end up getting a net extra shift here. You push that through, you would end up having a shifted PNR measurement, which you don't want to do. So you actually have to physically undo it probably here. And that would be the only spot you have to visit. So what that does, you can think of it as I'm kind of recentering my state in phase space before doing subtraction. Yeah. It is not always an even cat. It's sometimes an odd cat. There's actually, in general, this fringe will kind of scan, and it's somewhere in between.
Yeah, well, the reason I was asking is that does this quantum channel stabilize the system to a fixed state, or it will be even or odd? It's more like a quantum instrument with some classical outcome you need to take into account to know what the output state is.
It's a fixed amplitude with random phase, but you can know it. You can calculate it based on all
based on the measurement outcome.
Yes.
Okay, great. Thanks.
Can I go? Okay.
No, Raj, you can't go.
So here, when you subtract a photon, do you keep the same beam splitter, or you adaptively change it at each stage?
Keep the same beam splitter.
So if you sort of change it, could you reduce the number of steps?
Likely. Actually, so the fastest you can do is if you don't do a beam splitter at all. So this is kind of interesting. If you could assume that you can re-squeeze, actually, if you squeeze right before here and replace this with just PNR and squeezing, then you can make it in one shot, but it's highly probabilistic. But then it's also, you have to re-squeeze and you have to detect a large photon number. So you can imagine the tunability of the beam splitter basically says, how much am I doing quadrature measurement versus how much am I doing a photon number basis measurement? And the stronger amounts of photon number basis measurement you do, the more you sample in that kind of space. And so you get more phase space damping from finite squeezing Gaussian noise that comes in, but you can actually increase the non-Gaussian faster. But then you also have to detect larger photon numbers.
In that case, you are effectively doing a squeezed number state basis measurement.
Yeah.
Got it. Thanks.
Any other questions? If not, let's thank Miller for an excellent talk.